Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems IISc. Today's talk is by Dr. Sudhir Dixit, and he will be speaking on network slicing in 5G and beyond and its application to bridge the digital divide. Dr. Sudhir Dixit is a co-founder, senior fellow, and evangelist at the Basic Internet Foundation in Oslo, Norway, and heads its US operations. He is also associated with the Academy of Finland 6G Flagship Program, led by the Center for Wireless Communications, University of Oulu, where he is a docent. From 2015 to 2017, he was the CEO and co-founder of a startup, Skydoot Inc. From 2009 to 2015, he was a distinguished chief technologist and CTO of the Communications and Media Services for the Americas region of Hewlett-Packard Enterprises Services in Palo Alto, California, and the director of Hewlett-Packard Laboratories India in Palo Alto and Bangalore. Before joining HP, he held various technical and leadership positions at BlackBerry, Nokia, NSN and Verizon Communications. He has been a technical editor of IEEE Communications magazine and is presently a board member, working group chair and vice chair for Americas at the Wireless World Research Forum. He was on the editorial board of IEEE Spectrum magazine and presently on the editorial board of Springer's Wireless Personal Communications Journal. He is a co-chair of the CTO working group of the IEEE Future Network Initiative. Dr. Dixit has published 9 books and holds 21 US patents. In 2018, he was appointed a distinguished lecturer by the IEEE Communications Society. From 2010 to 2012, he was an adjunct professor of computer science at the University of California, Davis. A life fellow of the IEEE, fellow of IIT and IITE, Dr. Dixit holds a PhD from the University of Strathclyde, Glasgow, UK, and an MBA from the Florida Institute of Technology, Melbourne, Florida. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Dixit directly at the end of the talk or type them in the chat box and we'll moderate it with him. Over to you, Dr. Dixit.
Thank you, Anusri, for a very kind introduction, which was a long one. So thank you very much for the time. And thank you, everybody, for attending this seminar. It is 6:30, 6:45 a.m. here in California and 7 p.m. in India. Sorry that this talk could not be held at a more decent time for everybody in India. But we have these time difference constraints, as you know. So in any case, I'm delighted that so many of you have joined to listen to me. As Anusri mentioned, the title of my talk is Network Slicing in 5G and Beyond and its applications to bridge the digital divide. So that is the title of my talk today. I presume that the talk will be of 1 hour duration, and I would like to finish it in about 45 minutes or so, or 50 minutes, leaving about 10 minutes, 15 minutes for any questions and answers that we may have. So with that, let me move on to the next slide. Can you see the next slide?
Yes.
Okay, because I've had this issue in the past that the slides were not advancing. But anyway, the outline of my talk is as follows. I'll provide a bit of a background of 5G and network slicing. what network slicing is, what are some of the key network slicing initiatives are around the world, how can network slicing be applied to rural connectivity, and I would summarize my talk. I should mention at the outset that network slicing is a very complex topic because it touches very many domains, right from physical layer to services layer, and has, even though it offers a very attractive business model for the service providers, but technology that goes with it is quite complex, and to make it happen in a networking commercial environment, and I'll touch upon that. So let me mention this. Okay, sorry. Let me, I don't know how to get rid of this. Okay, so the point here is that the next decade is going to be very different, and we have seen a sea of change over the past decade as well. That this model of one size fits all for network is not going to be working. It's already not working with the congestion that we see on the network, especially with people consuming a lot of video, watching movies, and so on and so forth. So the best effort solution for all kinds of applications and all kinds of data is already not working. So something needs to be done. So the network slicing breaks the old model of one size fits all. And the old architecture that we have had, which was based on a network of entities, that you have a number of network elements, and there was a well-defined architecture that was anchored into physical positioning of various devices. That is going to evolve, it's already evolving into network of capabilities architecture. What capabilities you can provide, irrespective of where those capabilities and services are coming from, especially in a cloud-based environment connected through very high-speed transmission networks. Network for connectivity model is going to change to network for services model, and specialized bespoke network infrastructure, that one infrastructure built for one kind of services and another one built for another type of service, because there are different kind of requirements. That is also going to change and already changing to a common and shared network infrastructure to provide agility, flexibility, efficiency, availability, and economy of scale by being able to share different type of networks, different kind of services over a common platform. So that is a transition that is fast in the works, and is going to pick up momentum. So this is the going mantra right now, and is going to be happening more in the future. So what is network slice and slicing? So one can think of network as a service, with the cloud being there. We have already heard about software as a service, platform as a service, and so on and so forth. So why not network as a service, which is built around cloud, edge servers, and so on and so forth. So there are several, when I was researching for the talk, to be very specific, I was looking at definition. What is there one accepted definition of network slicing? And different people use different definitions. But there is one simple definition that is adopted by 3GPP and GSMA, which is a network slice is a logical network that provides specific network capabilities and network characteristics. So basically, a network slice is a logical network built on a shared infrastructure that provides a purpose-driven network for a set of applications, which is very similar to the evolution that we have all have seen in virtual LANs with our laptops, where we have virtualized disk structures, and how the computing and storage resources are broken up. So this virtualization has been going on for a very long time. It's not a new concept, but it has been slow to be taken up by the networking community over the last 10 years or so. So again, to reiterate, network slicing is a network architecture that enables creation of multiple unique, logical, virtualized, and independent logical networks end-to-end over a common physical network infrastructure. Each network slice is an isolated multi-domain end-to-end network tailored to fulfill diverse requirements requested by a particular application or a user. So potentially we can have a network slice that serves only enhanced mobile broadband. It only serves only Internet of Devices, or another slice could only serve only ultra reliable and low latency applications. So one could potentially build a different kind of slices over the 5G infrastructure. And when we talk about multi-domain here means that the end-to-end connectivity is across different service providers and network providers, and also across different parts of the network, even if the network is owned by a single operator. So network slices typically span across multiple network domains such as access, core, and transport, and across multiple operators, and often across regulatory boundaries, because these networks also go across states, they go across countries, which have different regulatory boundaries and requirements that the service providers have to adhere to. And some of the main concepts that network slicing employs, they are software-defined networking, as I'm sure most of us have heard about. SDN allows softwareization of networking, network function virtualization, cloud orchestration, where you can orchestrate software appliances or software elements out of a more generic hardware to have routers and deep packet inspectors and so on and so forth, and automation. Allowing mobile network operators to quickly roll out network slices to support a specific application, service set of users or network. So networks, even before the arrival of network slicing, the concepts of SDN and NFV, they have been floating around, and cloud has been with us for good 15 years or so already. So all of these things have come together at the same time, that have given rise to network slicing. So even before the concept of network slicing came around, SDN and NFV was being utilized to make this telecom infrastructure more softwareized, similar to what has happened in the IT industry with the softwareization of the data centers. Because up until 20 years ago, these data centers used to be extremely expensive, because each application on an operating system was running on a server. And now with the arrival of virtual machines, it has become possible to run many different virtual machines on the same hardware server. That allows the data centers to be run up to about 70-80% efficiency, as opposed to 25-30% as it used to be before. And in addition to allowing for backups and mirror sites and so on and so forth. So virtualization is a big thing. Is going to revolutionize telecom. But this concept of an NFV and SDN that was born in October 2012. So NFV SDN is a rather new concept, only 10 years old, when about 10 or 12 companies came together and they introduced the NFV call to action document, which was followed up by ETSI, giving it a momentum from the standardization point of view. Some of the key organizations that have been driving virtualization and SDN, actually NFV, they are ETSI, 3GPP, and Open Network Foundation. So NFV is a network architecture concept that uses the technologies of cloud computing and IT virtualization to virtualize network functions. And SDN is a closely related concept to build data networking equipment such that control plane is centralized and data plane is distributed. So SDN is basically provides a control plane which allows the definition of network elements, softwareized network functions in the data centers out of the more standard hardware and interconnect them in a way that an end-to-end network is configured rather than a network built of hardware custom equipment. And SDN concept has been driven by ONF, Open Daylight Project, OpenStack, and many other foundations that have been behind it. And open flow is a concept that I'm sure some of you, or if not most of you, know, that provides the standard communication interface between the control plane and the forwarding layer of the SDN architecture, and is standardized by the ONF. So open flow is a communication interface between the SDN and the forwarding plane, where the data flows from one end to another end over softwareized network elements. And some of the drivers for NFV and SDN have been that it allows rapid service innovation and faster time to market, reduction in cost, reduced power consumption, vendor interoperability. Because previously, if an operator bought an equipment from a network provider, a network manufacturer, then they end up buying equipment only from that manufacturer. And with the standardization and softwareization, it becomes possible to mix and match equipment and the software solutions from many different providers. Okay, so transformation towards software-defined mobile network is a reality, and it is revolutionary, and is going to change the telecom infrastructure as we have known before. Just to introduce the topic of virtualization very quickly, what has virtualization done for the IT industry? It has brought huge efficiencies to companies like Google, Facebook, and any organizations, including government or the universities, to be able to virtualize their data centers. So if you look on the left-hand side, the traditional approach up until 15 years ago was that you'll have a certain application running on a certain OS, which is tied to a hardware. And then every application and every instance of that needed a backup in the data center. So it was, and each one of that a hardware system was running maybe about 15, 20, or 30% efficiency, and the rest of it was not being utilized. So what virtual machine technology has done is that the hardware resources, which are generic, like CPU, memory disk, network interface card, and display, they have been enabled through a hypervisor technology that allows multiple virtual machines to be running on the same hardware resources. So one application may be running on one OS, another application could be running on a different operating support OS, and a third one may be running on a different OS, and they all could be running on the same hardware resources, and that increases the efficiency of operation to up to about 70-80%. So this has happened in the IT industry in a big way, and it is only happening in the telecom industry now. Okay, so what is NFV? It basically says that the classical network appliance approach, which was routers, deep packet inspectors, firewall, routers, SGSN, GGSN, they used to be dedicated pieces of hardware. Now they all could be softwareized onto standard high volume servers and high volume compute devices and storage devices to emulate, to virtualize each one of those network elements in the data centers and interconnect them through fiber or through maybe wireless interconnectivity. So this is what NFV has been doing. So this is another representation of ETSI's reference diagram for NFV, whereby there is a NFV management and orchestration platform or software, which really interacts with different kind of hardware resources, compute resource, storage resource, network resource, and creates a virtual compute, virtual storage, virtual network, which gives rise to NFVI, network function virtualization infrastructure, and out of which one could build these virtualized network functions. All these kind of functions could be built through from the NFVI, and these are called VNFs, and that has become possible by the NFV management and orchestration, that is also called MANO. So anyway, so the point here is that now there are manufacturers or suppliers of orchestrator, many different ones. There are different suppliers that will allow the creation of virtualization of machines. So it has really opened up the competition across the industry. I'll skip this in the interest of time. And SDN's basic concept is that it allows separate control plane and data plane. So control plane provides all the network intelligence, and current state are centralized. So the SDN knows from an end-to-end basis what is going on in different parts of the softwareized data plane, and it controls what traffic will go from which part of the network, from what entities, for which operator. And the next level of that was how can you interconnect these things to create a virtualized network by itself for a type of a service. So a type of a service, as I said, could be for enhanced mobile broadband, ultra reliable and low latency communication, or it could be just for video, or another virtualized layer, or another slice could be just for text and images, not for video, to provide the quality of service that people expect from their service providers. So anyway, I wanted to share this diagram just to introduce to everybody as to the difference in the parameters, the traffic parameters, or the aspirations going from 4G to 5G to 5G to 6G. So if we look at this diagram that shows that the inner spider diagram shows the technical parameters of 5G standard on different dimensions, like what the peak rate is expected to be, what the user experience data rate is going to be, and what those rates are expected to be as people start working on 6G. So this is comparing 5G with 6G. So the aspirational goal of 5G was 1 millisecond, and the goal for 6G is going to be 1 microsecond. So this basically shows how the technology has been improving over time. Okay, so these are some of the revolutionary things that are happening, and and what has happened even in 5G, that 5G is being positioned, or has been marketed or envisioned to support different kinds of use cases on the same network. So the expectation is that it will support autonomous driving, remote surgery, electric grid control, a number of sensors that will be supported over 5G. And they all have very different kind of requirements of bandwidth and of latency. So for instance, if we want to utilize, if we want to use 5G for electric grid control, the requirement is perhaps about maybe 1 millisecond latency, and the bandwidth requirement is not that much, because it's the data, that the amount of data that flows is small, so there is one set of requirement for it. However, if somebody is running virtual reality, then the bandwidth requirements are quite significant, and also the latency is also significantly higher as well, significantly lower. Oh, sorry, significantly higher. So it depends on where the what kind of application one wants to run on a 5G network. So so in a nutshell, the 5G is expected to run different kinds of use cases on one network, and that would only be possible if we can partition the network in many different slices. Okay, so I wanted to share this slide that many people think that mobile networking, mobile communication, as we go from 4G to 5G to 6G, it's all about wireless connectivity, and it's only offers opportunities only for the for folks who are working in the telecommunication computer industry. But the fact of the matter is that it has already created a lot of opportunities for people working in electronics and materials, people working in wireless communications, people working in computer science and engineering. So 5G or beyond 5G is about many different domains and many different technologies. So, for example, in 5G and beyond 5G, the aspiration is to have foldable displays, for example, and that requires different kind of research in material technology, nanotechnologies. If we have many different kind of transceivers running on a mobile device, whether it is a tablet or is it a smartphone, we want to be able to run these many different antennas and many different kind of receivers on a small form factor, which are tunable across different ranges of frequencies. So it requires a lot of work on RF modules and how do you package those things. So there is a lot of work for electronics and materials folks who are doing research, and also who are in the development phase of these technologies. Similarly, for computer scientists, there are a lot of opportunities for image and signal analysis through for authentication, for video-based applications or imaging type of applications for smart sensor analytics, privacy and security, big data analytics. So the point here is that as we go from one generation to next, there is a need, and there are opportunities for significant research in many different domains, not only on the radio technology that some people think is about that, but that's not the case. Let me touch upon the spectrum spectrum requirements because it determines the capacity and also the speed of communication. So the whole spectrum is partitioned into three different bands: a low band, mid band, and high band. So low band is up to about 1000 megahertz. Mid band goes up to about 6 gigahertz, and high band is from 24 gigahertz to 40 gigahertz. And some of the bands between 6 gigahertz and 24 some of the bands is unusable because of the characteristic of the atmosphere, and I'll touch upon that a little bit. So the lower frequency band that one is operating on, the longer these the signals can go, which basically means that your coverage area is more. And if coverage area is more, then it can only support fewer number of users if we want to give them all enough capacity. So capacity for each user and for each cell site gets limited if you're operating in the low bands. And there are 5G offerings already in the US and different parts of the world where the mobile operators have rolled out 5G in the low bandwidth region and also in the mid band region. So there are combination of these cell sites that are already operational at this point in time. I won't go into this. The point here is that up to 6 gigahertz is used by cellular, and from 6 gigahertz to up to about 57 gigahertz is potentially available and has been given out by the radio administrators across the world. However, there are certain parts of the spectrum that are not usable because of the constraints imposed by the atmosphere. That oxygen will, the oxygen absorption will attenuate the electronic signals, and water vapor absorption will affect the electromagnetic signals in these 164 to 200 gigahertz. But the point is that if we go from the lower band to the higher band, the cell size become very, very small, and also the signals cannot penetrate through trees or through walls and other physical surroundings that the signal will encounter. So some of the key concepts of network slicing are as follows. Okay, so just to recap again, the 5G has been classified, or from a network slicing standpoint, there is a radio access network, there is a transport network, and there is a core network. So radio access network really concerns about the up until the base station and how the resources are allocated. A transport network concerns the connecting the base stations to the core network, and it would potentially use the optical fiber, ring network, or maybe microwave, and it will have three different layers: access layer, aggregation layer, and core layer, and that will connect with the core network. So transport layer and core network. So there are three different parts of the 5G here. And after the core network, it connects with the broader internet backbone. That is how the structure, the architecture typically would look like. So some of the key concepts in network slicing are that an infrastructure owner will own the infrastructure, would own the hardware, and the infrastructure owner can potentially provide a slice to whosoever wants it for type of services, or a service provider can lease the infrastructure from the infrastructure owner and create its own slice and offer it to the end users. Or the enterprises could request infrastructure from the infrastructure owner and develop their own slice and build an enterprise network to interconnect many different sites. And one typical example, it could be the central government could build their own self slice for their own internal applications or internal slice, and also external facing slice as well for the users, for the community. Uh, and those people who use the infrastructure, they are called infrastructure tenants. So the those folks who use the many different slices from the same infrastructure owner, they become the tenants of the infrastructure. So these are some of the concepts or the terminologies that is being used in the network slicing community. And then there are different types of partitions one can have. From the common hardware infrastructure, it could be physical partitioning if somebody wants a very secured system, resource-based partitioning also, and or overlay, underlay based partitioning. But if the slices are made out of partitioning other physical infrastructure, then it is no different than what we have it today, or we have had it classically up until now. And the problem with the physical partitioning is that the efficiency of the physical infrastructure is very, very low. But if only the resources are shared, then also the efficiency is low. But it is much better than physical partitioning. With resources, I mean that we have softwareized some of the network functions, and they have been interconnected using the NFV technology. Or if we can build overlay and underlay network also, that gives even better efficiency, even better. So anyway, so typically these are some of the bandwidths that are being utilized. So from the base station to the transport network or the access layer, the typical bandwidth is about 10 gigabit that is being used, and 50 gigabit per second link at the access layer. So the access layer will typically have a kind of a ring architecture that will connect many different base stations to the transport network. It could be a ring network, it could be a star network, depending upon the environment. And 100 to 400 gigabit per second layer, the aggregation, when the traffic is aggregated, and up to 400 gigabit link at the core layer. So these are the type of or the extent of the capacities that we are talking about. So these are different type of network slices that we have shown. That there are many different type of network slices. Provider internal slices, provider slices as a service, external provider managed slices, external tenant managed services. So basically in provider based, meaning that a service provider would have an internal slice for their own operations, or it would create a slice and offer it to somebody else. So there is a mobile operator who would create a slice for ultra reliable and low latencies applications, and will provide it to its users or customers. Or it could be an external provider, meaning it could be a third party, a new kind of MVNO, who can, mobile virtual network operator, who can provide a slice and can offer it to their users. Or it could be an external tenant. A tenant can, which is the slice owner or the infrastructure owner, who can provide a slice also and offer it to its own external users. as tenants. So these are the many different kind of slices that could be delivered. One of the biggest benefit of slicing technology going from best effort is that in best effort, the business model remains the same. They're selling the data packages. So basically, depending upon how much data is consumed, that is what the customer gets billed for. But if it is service-based or slice-based offering, then there could be different models of pricing. So a customer who is requesting ultra reliable and low latency can be charged higher for the same number of bytes consumed, as opposed to somebody who, some customer who is utilizing a slice for IoT and machine-to-machine communication. So there could be different kind of tariff offerings for different kind of slices. And also these slices could be billed differently to different enterprises or different types of customers. So for example, a customer in the medical community could be charged differently as opposed to somebody in the transportation industry. So it opens up new revenue opportunities for the operators, and those are some of the big incentives for the operators to push for network slicing. Okay, in the interest of time, I would have to skip this. Basically, it is showing that at the transport layer, we had three sublayers: access layers, aggregation layer, and core layer. How can, what does it mean from a slicing standpoint? So access layer here is on the left, and he's a metro, which is the aggregation layer, and there is a IP core, which is the core network. And the access layer basically shows that you've got the base stations, which connects with the it may be a campus-based network. It connects with some kind of a router, some access devices, and they go to a ring architecture, and then they go to a metro network for aggregation. And each one of these, wherever these network boundaries meet, there could be a server, mobile edge device, or the servers could be there, so that the services are served right from the edge of the network. So the closer you can serve the customer, the lower will be the latency. So these mobile edge computing, that has a big role to play, because now we can interconnect these different layers through very high speed optical WDM technologies, and we can position these servers closer to the network. So mobile edge computing plays a big role in network slicing as well, to deliver the aspirational performance that have been talked about and have been promised in 5G and beyond 5G technologies. This is another representation of 5G network slicing. What is driving network slicing? I already touched upon it, that 4G networks did not enable the range of services that the future requires, and 5G will enable faster and more flexible services over a shared network. So this basically shows different kind of applications, such as communication for entertainment, communication, and entertainment, retail, shipping, manufacturing, a vertical, automotive as a vertical, and they are utilizing different kind of slices. And these slices are called mobile broadband slice, machine-to-machine slice, reliable low latency slice, and so on and so forth. So basically, how can you virtualize the 5G access network, 5G network, and create different slices? I've already touched upon it, so I'll skip it. Basically, the point is that network slicing meets the requirements of different vertical industries to serve a variety of use cases and application scenarios. Okay, so some of the major requirements of slices are that these slices need to be self-contained. These slices need to be mutually isolated. They should be manageable and programmable, and they should support for multiple services also. So one of the biggest concern is of security of data, of one traffic of one slice overflowing into another slice, how to provide the SLA, and how to provide the guaranteed quality of service within a slice to a user or a set of users in a secured and trustable manner. Okay, so I already touched upon it, so I will skip some of these points. So basically, it's the same thing that we have 5G, next generation radio, there are edge clouds, this transport technology, and it's connecting with the 5G cloud native core, because the cloud in the core network is taking care of service authentication, of billing, and capturing all the accounting information, and so on and so forth, which used to be done through dedicated servers, AAA servers, for example, which have been softwareized now in the 5G native core. There are many different projects and standards activities going on in this. In the Europe, there have been many different projects that have been listed here: Sonata, 5G, EX, NECO. There are many different standards activities in network slicing, namely from ITU, that have been driving it, but the actual work has been going on in 3GPP and ONF, ETSI, Broadband Forum, IETF, ONAP. So there are many standards organizations that have been collaborating with the 3GPP and ITU being the core of integrating all of these things to develop new releases of 5G. For instance, the first mention of network slicing was in release 15. Then there were more specifics of network slicing that came in release 16. And now there are more capabilities and more specifications coming out in release 17, and so on and so forth. Okay, I will skip some of these slides. So this is the abstract view of network slicing architecture. You have infrastructure layer, network function layer, service layer, and they're all controlled by an network slice controller or orchestrator that will create the slice end to end. So as you will see, the network slicing technology is extremely complex. It runs across many different layers, many different domains, and it is continuously evolving. Okay, I'll skip some of these slides. Okay, then what about slicing for Wi-Fi based radio access networks? So there have been many different papers on being able to define many different SSIDs on a single access point. A single hardware access point could support many different SSIDs, and each SSID is specialized for or being considered as a slice for a type of a service. For example, if it is mobile broadband type of a service, entertainment type of service, that could be one slice. Another slice could be for ultra reliable and low latency application. Another one could be for machine time communication. So one could potentially have many different SSIDs that a mobile user or a laptop user could connect to on the access points. And as a user moves from one Wi-Fi access point to another access point, the handover happens in a seamless manner from one SSID, from one access point to another access point. And then there is this notion of virtualized Wi-Fi access points. So one could have a virtualized access point that could move over from one location to another location. You could potentially allocate these resources statically for each slice through SSIDs, or one could have a dynamic resource allocation depending on network conditions and desired KPIs that could be done. But very little work has been done on network slicing for Wi-Fi access points. But it is not to say that people have not looked into it, because Wi-Fi is an integral part of 5G standardization. So that has also been studied as well. Okay. Creating and running a new network slice, there are 4 main actions. How to configure a new network slice instance using standardized templates. So basically the point is that in the RAN, in the transport network, in the core network, there are different kind of templates that have been standardized. So if I go back, if we leave it at the very abstract level and a lot of flexibility, then it's very hard to make progress. So these 3GPP has defined many different templates for RANs, for transport network, and for core network. And these templates are selected by the orchestrator. And these parameters are defined for these templates for each domain of the 5G network. With the parameters, and these are interconnected by the orchestrator to create an end-to-end network. So that is how it is expected to be done. So how to create a new network slice on demand using standardized templates? Operate and manage a slice dynamically. How to isolate and secure these slices, how to gracefully change the size of the slice. So how do you do prioritize readjustment of slice, maintain an audit log so that if there is a security breach or denial of service, one can go back and find out what really happened, how to do the accounting of how the SLA is being provided, is it being delivered or not, and that is done through capturing a lot of accounting information. This is the 3GPP reference architecture for network slicing. We don't have the time to go into, but this is all commonly available information on the web. This is the overall network slicing architecture that has been utilized by 3GPP and ITU to define network slicing standards. Provisioning, operations, and management. The life cycle of the network slice, how do you define it, how do you manage it, how do you deploy it, and how do you remove it. So that has been standardized also in different standards bodies. Monitor network slices for SLAs, management function at each domain and across domain for individual slices. What are the mechanisms to support multi-tenancy while sharing management resources? So each network slice is managed through its own management resources, but there is a common management resource that is being shared across across many different slices by many different tenants. So how to share it in a non-interfering and secure manner, how to offer isolation and security, maintain an audit log. Okay, I already touched upon that. So there are many different research opportunities. So when I and some of the colleagues I worked with at IISc and other places, we scratch our head and think, what are the research opportunities? So actually, there's a lot of engineering challenge to be diverse and to be able to meet so many use cases with varying requirements. So network slicing, to tell you the truth, is an engineering challenge. How do you implement it? How do you define the interfaces? How the different entities operate with each other, and so on and so forth. But from the research point of view, if you dig deeper, there are 5 different research topics that come out. One of them is dynamic resource allocation for slices. So obviously, if you have a slice in the radio access network for radio resource, and a user is moving from one site to another site, one location, then the handover has to happen in a dynamic manner in a slice with along with the agreed SLA. So dynamic resource allocation while maintaining the characteristic of that slice is a big research issue. Mobility management while delivering RAN, SLA, and quality of service. So if you do static resource allocation, it is an easy problem when the users are not mobile. And up until now, network slicing has been experimented with and has been proof of concepts have been demonstrated only in the static manner. But in the mobile environment, there have been only few, if any, demonstrations of network slicing. Another big research problem is how to do slice isolation at the infrastructure level, at the logical level, at the security level, privacy and operation support level, and so on and so forth. So on a slide and a concept level, it is easy to say that the goal is to provide slice isolation, but how do we actually do it? What are the research issues? Then dynamic slice SLA management vis-a-vis variable traffic, because the traffic is continuously changing in a slice. Some users are coming online, some are taking out their connection. So how do we do this dynamic slice management? And quantification of how a slice is functioning. How do we quantify how well it is doing? So quantification, rather than the concept, is a research issue as well. I don't think I have time, but okay, I'll just take 5 minutes very quickly. That rural connectivity using multi-tenancy with 5G network slicing is a big opportunity. And the main thing here is that there is the main concept here is that somebody builds a network infrastructure in the rural community. So he or she becomes the infrastructure provider and leases out the infrastructure as a slice to mobile network operators or to other service providers in the community to offer services. So there could, through the slicing technology, one infrastructure provider could offer the infrastructure to many different service providers who could be big operators in the metro or in the urban areas. So there is a sharing of the infrastructure of the rural area, which become incentive for the infrastructure provider to build the infrastructure in the rural community. And we all know we had a very nice presentation by Professor Satyam Agarwal from IIT Roper in January, who talked about bridging the digital divide. That about 3.5 billion people still are unconnected, and today we are talking about 5G and so on and so forth. So how can we use 5G? What is the role of 5G to connect these unconnected or underconnected communities? So with network slicing technology, it becomes much more commercially viable for an infrastructure provider to have a better business proposition to build the infrastructure and offer services. And there's a good book on price of inequality is huge. If we don't connect all these people, because they don't get the health information, education, decent work environment, and so on and so forth. We all know that there are many challenges of bridging the digital divide. We all know that, so I'll skip this. Low population density, sparse and clustered settlement, price benefit comparison is not the same as for urban suburban areas. So we need different kind of business model. Most of us have seen this diagram for 5G, where the three main goals were enhanced mobile broadband, massive machine type communication, ultra reliable and low latency communication. But there should have been one more goal of 5G, that should have been connectivity for all, and that should become an integral part as we go beyond 5G towards 6G definition. This picture basically shows can we build a network architecture whereby we provide free service to the rural communities. So we define the services that we call digital public goods, or important type of services for financial transactions, education, healthcare. Some of those could be called digital public goods, and they are delivered free of cost. And people who are using internet for entertainment, like Bollywood movies and so on and so forth, that we call heavy DPGs, heavy digital public goods, and low digital public goods. And low digital public goods are delivered free of cost. But heavy DPGs and low DPGs, if they are stored locally in the rural areas on the edge servers, in the rural community, they all are delivered free of cost. And as the request goes to the backhaul, to the backbone of the internet, that becomes a chargeable service to the end user in the rural communities. So we can have an attractive business model whereby we offer some services are free, and we offer the other services through a paid model. So that becomes commercially feasible. So we can think of providing a network slice that only supports a certain type of services and certain types of data, non-video data, that is offered for free, and the other ones are offered through other paid or premium network slices. Okay, I'll skip this. I just share that if we look from a rural community point of view, the rural network is typically made up of Wi-Fi hotspots. They have got ports, local VoIP server. There could be a public data office where people could go to, like gram panchayats, and there is some kind of a switch. And we use TV white space or long range Wi-Fi as a transport technology to go to the backbone. So this is, we can potentially segment what we were looking at early on, RAN. So this becomes the RAN for the rural areas, for the village, and we create different network slices. So infrastructure or neighborhood network provider provides the infrastructure, and there are MNOs who would lease the slices from the INP, and they become their tenants, mobile network operators, and offer services to the users. And then that will provide some competition also in the village, rural, and there could be some government subsidies that could be offered to the infrastructure provider as well. Okay, I'll skip this. This is the last slide I have. Some of you may have heard about this, I would call it revolutionary interface that has been approved by the government of India, which is called the Prime Minister's wireless access network infrastructure, PM-WANI. And it is very similar to the PCO model we used to have in India. If you remember, up until 15 years ago, 10 years ago, people used to go to PCOs and they'll make the phone call. So there were PCOs everywhere in every street corner. So why can't we have this PDO model that we create a public data offices? So these are Wi-Fi access points, which anybody can offer the street corners and in rural areas, that people can walk up and connect their devices. And these Wi-Fi access points are connected to ISP gateway. They have to connect with an internet service providers that connects with the internet. And there are three other entities that are there in this architecture called public data office aggregator and application provider network. The idea is that there are no regulations. The government has freed up any regulatory requirements so that anybody can set up these PDOs. They can offer these offices, these PDOs, even from a room in their house. You know, they, like the doctors have their office on the front room, or there are people offering tutorial classes. So one could potentially have these PDO where people can walk to, and they connect with an ISP. And there's a PDO aggregator who does the job of authentication, does the job of accounting, subscribing. So PDO, a PDO can become a subscriber, can come online through a PDO aggregator. An application provider is the one who provides the web interface. So basically, when you go to a PDO can have an agreement with an app provider to have this front-end interface to the user. And these all have been standardized. And this PM-WANI central registry, this registry is maintained by Skydoot at this point. And the PDOs, they have to register with the central registry. The app network provider, they have to register with the central registry also. So here, so if a subscriber is a customer of PDO1, he or she can roam to a PDO2, PDO-N. So there is a roaming also provided in this. And there is a roaming agreement across these PDOs. And that information is maintained by PDO-A and PM-WANI central registry. So if I go to a certain location, so it is like the Uber of the taxis, or Uber of food delivery. So I have a service whereby I can say the nearest PDO I can walk to, I go there, and I can walk the next one I can go to, and there is and I can seamlessly roam. But the great thing about that is there are no regulations involved. The PDO Service provider doesn't have to pay to the government, doesn't need to get any licenses. They only need to register. Similarly with the PDO, so there is no bureaucracy, there is no overhead, and there is no cost, which makes it very cheap and cost effective to the PDOs to establish their offices. And that was approved in 2020. And there are hundreds of PDOs already installed. One can go to the website here and download all the documents and the standards that are available. And there are many countries also which are very much interested in adopting this architecture as well. So this is revolutionary from the Indian perspective with the vision of Digital India, with the goal of having maybe up to 10 million Wi-Fi access points in India within the next couple of years. So in summary, network slicing is a powerful concept. A business value is unquestionable. It is very complex in standards development and implementation. There are too many moving parts which have to come together. There's a need for consistent chaining that has to happen across network slicing domains. In the area of dynamic isolation, management and security are the major challenges. How do we automatically create and dynamically manage these slices, which is a must and require a lot of work. There are only limited proof of concepts and implementations that are known. There are no commercial rollouts of end-to-end slices as of today, but there is a lot of interest in the industry to create these network slices across 5G network and also across the broadband internet also. That should be part of the ecosystem as well. So with that, I'll stop here, and sorry I took too much time here.
Thank you, Professor Dixit, for the engaging talk. We can now take questions.
Good morning, Professor Dixit. Can you hear me?
Yes, I can. Yeah.
Okay, this is Joy here. Thank you. I had just one question, at least one to begin with. There was one part of the talk in which you were mentioning about the opportunities in very, very distinct domains that have arisen because of the 6G activity or moving towards the 6G activity. So some examples that you gave were materials and even electronics. Now, there was also a mention of computer science in that. So are there some examples in the computer science domain which are like opportunities in this emerging 6G kind of world?
Yeah, so we all hear a lot about the use of AI and ML and analytics. How do we do that in the networking environment? So if I can go back, I don't need to share the slide, but when we talk about security issues, privacy issues, customer profiling, context-based advertising, that all involves a lot of data gathering, analytics, machine learning. So it's all about computer science, actually, to tell you the truth. Yeah. And because all being done on servers, the algorithms, I would say that there are a lot more opportunities in computer science and electronics than on the radio side. Because, when we talk about softwareization, it's all about where the edge cloud is going to be, edge servers and mobile edge computing. Once we go from the radio part, radio part only provides this tetherless connectivity.
Right.
So we are connected in a mobile manner wirelessly. And once you hit the terrestrial part, then it's all about what do you do with it, you know. So I think it's more computer science, analytics than actually electrical engineering. But electrical engineering is very much there because of the need for nanoelectronics, miniaturization, signal processing. So, you know, having these antenna heads, you know this very well. We have got these antenna heads where you just collect the signal, the analog domain, digitize it, send it to some central location in the cloud and do the processing there in baseband. So there is lots and lots of work on signal processing in the antenna heads. How do you do the signal processing there in the analog domain, and how you do it in the digital domain in a shared manner again. So lots and lots of opportunities on sharing computing resources to do signal processing of connections of voice and data in a shared manner in broadband units. So signal processing is, you know, of course, we talk at a very high level about sharing the resources, but what do we do in those shared resources? You know, we talk about compute resources, storage resources, but we are doing something in those resources, and those doing something is analytics, about routing, about doing signal processing, machine learning, and AI, and all that. And that's where all these other domains from electrical engineering to computer science, electronics, they all come into play.
Right.
So there is an increasing need of interdisciplinary research, and but not doing research in a silo, but how do we interconnect these things to deliver something that is useful and generates value. Yeah, right. You know all about it, Joy.
No, thank you. It was a very perspective. It was very beneficial. Thank you.
Yes. So the challenge that happens now always is that I wish more and more people who are doing research, they get involved in the standardization process. Because people who are in the standards process, they are only talking about interfaces, about engineering aspect. But they leave aside what actually gets done, how it gets done, either as differentiation. You know, how does a manufacturer differentiate how they do it? They leave it to them. But people also need to worry about how do we, maybe there is an opportunity to standardize those things also. But with less and less investment in research in the corporate world, there is less and less participation of research people in these standards activities. And we all know standards is a very long drawn, expensive process where academics neither have the time nor the funds to participate on a continuous basis. But I think we need to come up with some model, some operational way to get engaged. So, for example, in India, like we have TSDSI and CHC. TSDSI is an approved standards body in 3GPP, and is playing a very important role now. Can we bring our research ideas to 3GPP and ITU through TSDSI? That may be one way to do it, which meets the goals of academic research, and also at the same time it drives the standardization process through some new knowledge, through new information. So there are opportunities there to innovate. And how do we do research? Yeah. Okay.
Thank you. Thank you.
Thank you. I know it's pretty late for all of you at IISc, 7:30, 8 p.m., running into your dinner time, family time. But if you have any questions, please let me know or send me an email. I hope I'll be there in the next couple of months that we can talk as well in person.
Thank you, Professor Dixit, for the enlightening talk. And thank you again for being a part of the seminar series. As discussed before.
Thank you very much, Anusri, Preetham, Joy, everybody else for the kind invitation for this talk. So I do appreciate the opportunity, and I hope I was able to touch upon some areas, some topics where there is potential for research, and how do we make that research more visible and viable from a standards perspective. So thank you again for the opportunity, and I look forward to continued collaboration and engagement. Thank you once again.
Thank you very much. Thank you.
Thank you. Thank you.
As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can visit our website for more details, and the links have been pasted in the chat box. The link to the recorded video will be also posted on the webpage. Thank you and have a great evening.